Welcome everyone to our fast pitch, the first of the summit, where we're going to be talking about the intersection of computing and storage. And you might be wondering, what does this have to do with energy? Well, it turns out a whole lot, because data centers are at the heart of this, and they are sucking up energy, and that's only going to expand as we get more into the era of AI. And with that, my colleague Peter de Bock is going to tell you about what those data centers are doing.
Thank you, Emily. I've gone over that quickly, but you can submit questions using the app. And I think the slides would come up. There we go. Glad to be here. We heard the secretary talk this morning about data centers, electricity to intelligence, fantastic, enormously growing field. If you read the news, you've seen that 500 billion is the amount of private investment going into Stargate project. 500 billion, let that number resonate with you. And those AI data centers will require gigawatts of power. But many people don't know that AI data centers need also a different kind of power. They need very robust power. My name is Peter de Bock, and I want to talk to you about supplyable backup power for gigawatt AI computing. I used to work on jet engine designs, extremely complex machines, and we would do very large calculations to estimate the flow through the machine, make sure it was very efficient. And we were talking about very large or enormous. This was 10 to the 18th flops, really large models that rivaled global weather models for the entire planet. Today, we live in the time of AI. Transformer chipsets allow us to do computational problems that are on the size of 10 to the 24th. Gemini, Llama, all these models are 1 million times larger than something what I called huge or enormous before. Now, what is the hardware that we need for these extremely large, 1 million times more than enormous kind of problems? And a single multi-core chip cannot hold such a large problems. You need hundreds of thousands of cores working as one machine. And that's very important to realize that AI can have not only a server, not only a single full rack, not only a full row, but perhaps the whole data center all working on the same computational problem. It's compute, communicate, the whole data center as one chip. And that is very different. And it's very important that each of these chips gets very stable power and keeps on operating. If one of them would fail, that's what would happen. We've all been there. Our computer crashed, we lost our work. We're like, what was the last time I saved? We've all been had that feeling. It's frustrating. If it happens to a gigawatt data center, it's a big problem. So let's summarize. AI requires really big calculations on many compute cores in parallels. And gigawatt AI cannot have power failures. It needs to have ultra-reliable power. And much more so than enterprise or other data centers that we might work on today. Now, how do we use that power in a data center? Let's zoom in. So inside data centers, you have these chips, transformers. They have hundreds of billions of transistors that each only require 0.65 volts, a very modest voltage, to do their bit flipping. Those chips get that power from 48-volt power supplies, and that 48-volt power supply might be connected to a 480-volt AC bus that's also connected to a UPS, or uninterrupted power supply. A UPS can be a backup provision for about 5 to 6 minutes, typically for a large data center. That's a lot of battery systems, but it only can do a few minutes. Of course, the standard way to power a data center is from the grid, but there's also a long duration backup option. And it's called diesel gensets. And diesel gensets connected to a large reservoir can typically hold up a data center for about 24 hours. Now let's do the numbers for a gigawatt AI data center. Now we're looking at 200 gensets, and these are not the small ones you can buy at Home Depot or Lowe's. These are large containerized machines, and if all 200 of them kick on at the same time, that is a lot of power. The efficiency of a diesel genset is around 40%, but the amount of fuel storage you need can be as much as 165,000 gallons of fuel. The other challenge you have here is that backup system, which is a lot of infrastructure, sits all the way on the right. And by the way, that backup system is similar to power a small city, maybe even a medium-sized city. That is a pretty darn good power plant. But it's got to move through all those conversion steps, almost like a mini grid, all the way to eventually deliver 0.65 volts to those chips. And every single step in that operation is another opportunity for failure. So not only does your backup system have to be very reliable, every single thing in between as well. Ideally, I'd power a DC voltage right at that chip core and get much closer to that, so I don't have to have all that equipment in between. So let's summarize. We have the electro backup, 6 minutes DC power close to the chip, wonderful. We have the 24-hour backup, fantastically long duration storage, but it's far away from the chip. Guess what? I am greedy. I want both. So I want to have DC power close to the chip. And electrochemistry actually allows us many paths to provide stable power. It's very uniquely perfect technology for it. If you look at a battery, it provides nearly constant power until it's depleted. What if you could refill that battery as it is powering your data center? And that's called electroactive fuels. Now, of course, you could say, why don't you just buy more UPS? And you could do that. You go from 6 minutes to 12 minutes to 18 minutes. It's not going to work for 24 hours. So I think that's not an option that's going to work in the near term. What you really want to get to is a system that you can supply similar to what we have for diesel gensets. It's not that different. But can you supply straight into the UPS that you can then later on fill with an energy supply either from a truck or a pipeline? Now you might say that's nice and all, but do these magic things really exist? I'm going to give you 2 examples. And the first one is organotrisulfide, a very unique compound. It's an organic compound that carries a sulfur molecule that you can pour straight into a chip. And this is really exciting work from James Picoul at the University of Wisconsin. And he calls this liquid batteries. You don't have to charge this battery, you just throw a fluid in it. This organotrisulfide actually then reacts with the lithium. And as long as you have lithium anode, and as long as you keep on supplying sulfur, you can run this system endlessly. Very unique aspect too is that the organotrisulfide dissolves the precipitates, and which allows you to run the system in a very clean way without any wear. What you do is when the fluid is used, you remove it from the system, and you can recharge it using a nuclear power plant, solar power plant, anything you want, and put it back into your reservoir. A very fun side fact, I said it's an organic fluid, so it does exist in nature. And it actually exists in green vegetables, cabbage and broccoli. It's the same fluid. So when your mother told you, eat vegetables because you're going to get more energy, she was right. Another example is power paste. This is a magnesium-based slurry that if you add water to it, it actually releases hydrogen. And this hydrogen can be used in fuel cells or other mechanisms to provide power to your data center. And the potential of these electrofuels is very high. You can see on the chart on the right that you have already densities that are significantly greater than the best batteries we have today, lithium-ion batteries. And we're even approaching or exceeding with these densities hydrocarbons. So if electrochemistry has a long way to go. So the next time this happens, I love this effect. Let's have some new ideas and come talk to me about electroactive fuels. Come see me tomorrow at Coffee with ARPA-E, and my colleague, Dr. Emily Kinser, will now talk about the next topic and will shine a new light on AI data centers. Here you go.
Great job. Great. Well, Peter gave you some optimism, and I hate to say it, but I don't want anyone to be alarmed, but we are surrounded right now. We are surrounded by photons. That's not a bad thing. They're helping project this presentation on the screen, making sure the email you just sent goes where you want it to go, and potentially finding the next TikTok for you to watch rather than pay attention to this presentation. I'm not going to judge. Photons are actually the workforce of our entire global information economy and information infrastructure. You can see Peter talked about data centers. Underneath the floor of this data center is a whole intricate superhighway of fiber optic cable moving photons and your information from one server to the other, back again, wherever it needs to go. But it's also the electrons that get all the credit for doing the work in the data center. They go to those fancy chips that Peter just told you about. And just as a reminder from your early science courses, electrons are particles. They have charge, but they also have mass. And they operate in serial, meaning they have to follow each other along. And when this happens, we generate heat like Peter was describing and like my friend Carlos is going to tell you a little bit about later. Photons, on the other hand, they're cool. They don't interact with each other. They're waves. They're not particles. They can move along and lose very little energy over miles, kilometers, even hundreds of miles. And they actually don't interact with each other. So that's a great thing. And they're fast, pretty darn close to the speed of light. Right now, photons are only moving the data, but we actually have the potential to get them in on the computing game through optical computing. Now, optical computing is not going to replace traditional electronic computing, but it does have the potential to be part of the solution in a high-performance computing environment like a data center to help reduce some of that heat. And like Peter just said, every little bit helps. So within a quick overview here, within a data center, we've got our servers, we've got that fiber optic cable running along the backbone, and we've got our computer chip in the guts of the server. So right now, though, the photons represented here in a fiber optic cable in blue, they don't even get in the front door. They are converted from photons to electrons outside the face of the server using transceivers or faceplate pluggables. You get how that goes. And then once we have the data in electron forms, we go to a printed circuit board and then to the processor chip. What's starting to become state-of-the-art in the semiconductor industry is called co-packaged optics or silicon photonics. In this case, we actually bypass that server front faceplate and go straight to the chip. We're not doing the processing in this case with the photons, but we can actually get them right in that neighborhood. And if we go to full-blown optical computing, we get 130x improvement in energy efficiency. Now, why is this happening? If you look at that link between the server and the printed circuit board, not that big of a link. In one server, there's approximately 400 meters, so a whole loop around a track that's out of copper wire that we can replace. And if you go to the processor chip, right now, in a state-of-the-art chip, there's 60 miles of itty-bitty tiny copper wires. So like Peter said before, by removing some of that copper and that heat, we can have an impact on data centers of the future and improve efficiency. So there's your energy tie. So taking a step back, you might say, okay, Emily, that sounds great, but what is it? How does it actually work? So taking a look first as a baseline for comparison, we have our traditional transistors that are working on the electron side. And we have our electrons in the source. And we have a gate in the middle, and it's called the transistor gate. When you hear the really tiny numbers in the semiconductor industry, that's what they're referring to as the length of that gate. And if we apply voltage, we can actually move electrons from the source over the gate to the drain, and that's how we flip a bit with a 0 and a 1. And I'll leave it to some computer scientists to explain to you why and what they do with our data from there. So with optical computing, this technology is so exciting because it's really in the nascent stages, and we don't even know all the mechanisms that we can use to make optical circuits or optical designs, the different materials that we can utilize. But one way we do know right now is called a saturation absorber. And if we send one wave of photons through the saturation absorber made of special materials indicated by those layers, the wave, the energy, those photons will actually get absorbed and no signal really comes out the end. Now, do you remember when I said that photons play nice and don't interact with each other? Well, I wasn't quite telling the whole truth, because if we send 2 waves of photons in at the same time, one of them is going to fill up all those spaces in that saturation absorber, so nothing really comes out. But the other wave, there's nowhere for it to stop, so it goes through pretty much completely intact. And that is the equivalent of our 0 and our 1 with optical computing. There's a few key enabling technologies that have made the time for optical computing now. And we have a path for the electrons with 3D integration. We have a path for the silicon photonics with our photons. And of course, I'm a materials engineer, so it all comes down to materials in the end. So we've got to talk about that. So the electrons have been going through something, again, Moore's law, we say every 2 years we get another evolution, another chip. There's decades of work behind this, and I was actually working on 3D integration way back in 2008, and I don't like doing that math because I feel really old at that point. But what most of the chips in our phones are made out of is what we call a flip chip with little solder balls. The analogy I like to use here is related to housing and neighborhoods. So the flip chip is basically that nice house at the end of a cul-de-sac. There's neighbors, but if you want to communicate between chips, house to house, it takes a little time. You have to put in effort, and you have losses in signal as you go. That wire bond, that's like the house in the neighborhood that never takes down their Christmas lights, so forget that. We're not going there. But moving on in the evolution, we get to what's called 2.5D. You can think of it like a duplex. We've got houses really close together. It's easier to communicate with your neighbors. There's a faster turnaround time and less resistance. And finally, last but not least, and has been in the works and demonstrated, but not yet completely in manufacturing, is 3D integration, where we can actually go to a high-rise condo building and have multiple floors involved and cram a lot more data density into that one footprint. So that's the trajectory for electrons, leading to, in the future, what we call heterogeneous integration, because we have different types of chips that we can build into a nice, vibrant neighborhood for inside our servers. One chip to pay attention to specifically is what we call a PIC, or a photonic integrated circuit. And spoiler alert, there's photons that go into that chip from our fiber optic cable. And this is where it starts to get really interesting. So in parallel, our photonics has been going down a similar path of evolution for, again, like 20 plus years. The faceplate pluggable here is represented with Gen 1. We're kind of Gen 2, Gen 3-ish, state-of-the-art, trying to get Gen 3 into manufacturing. And as we move down that chain, still several years out and still in research on the chip side, we have integrated lasers onto our chip, so we can generate and move those photons right there. Once we have that in place, what's next? This is where the potential comes in for optical computing, really that convergence of the electron technology and the photonics technology to get us where we need to go. Now, of course, I mentioned the materials, so there's a lot of materials innovations that we need to focus on to help make optical computing a reality. And it wouldn't be a technical talk if I didn't put some sort of table or chart in here, so take a look at that. What we use is called wide bandgap materials, and you'll notice that's about 10 times more. For the electrons, that means they can take the heat and they can actually take a lot of energy before you're going to get a breakdown in your substrate and in your chip. So they can go to really high voltage, the wide bandgap materials can go to really high voltages like applications for the grid. For the photons, they get a benefit too. We can send them through the material with our wide bandgap materials, and there's very little loss. Silicon, we're not getting our signal all the way through. A couple other materials-related areas where we need innovation is going down to the fiber optic cable. This has been the state of the art for 60, 70 years, and there's a lot more we can do at the fundamental material science with the glass and even with the sheathing around the outside. This, if we can get this right and make these available to be used for high temperature applications, we can then use optical computing in places like geothermal or geologic hydrogen, where we're putting our computing technology deep down in the ground. And last but certainly not least, because I'm a fan of sensors, we can actually take optical sensing is a more or less established technology. If we can integrate these optical sensors with our optical computing, we've got a whole system right there. And just imagine all the places that this could be used. It can seriously have a transformative effect on all of our lives and the energy ecosystem around the world. So now's the time to shift the paradigm, and in order to do this, we need to make optical computing a reality. We need to get all the scientific disciplines on the same wavelength. Our electrical engineers, our optical physicists, our material scientists, our computer scientists, and make sure that we are all laser focused on turning optical computing into a reality and getting those photons the recognition they deserve. And if you'd like to talk about this more or just curious, find me tomorrow for coffee with ARPA-E, and happy to do so. And with that, my colleague Carlos is going to tell you a little bit more about the heat of the data centers and what we can potentially do with it.
Nice job.
I went way over.
Oh, it's okay.
I don't care.
All right. Good afternoon, everyone. My name is Carlos Diaz, and it's really hard following Emily and Peter, so I brought some help with me. I brought my toaster from my apartment, and it's a really great toaster, but I want you to picture a toaster that's 100 million times more powerful, that's running continuously, and that's not making any toast with that heat. Well, that's what data centers are. So let me tell you about how we can use that heat to actually make some toast. Now, let's first think of the process of someone using their favorite AI tool. This sends a computation to a data center where electricity, which has an associated emissions footprint, is used to solve that computation. This process generates a lot of heat, which we typically waste to the ambient. And in fact, with AI growth, we could be wasting the equivalent of 70 nuclear plants worth of heat to the ambient. So I am here to instead propose that we should use this massive wasted energy to instead power carbon capture from the air. By doing this, we can capture almost half a gigaton of CO2 per year just in the United States, which we could then use as a feedstock to produce fuels, polymers, or other relevant advanced materials. And at the same time, we can produce almost 100 billion gallons of water, which would be enough for 3 million people. Now, you're hearing a lot about data centers and AI in this session. They're some of the most energy-intensive buildings in the world, and as a consequence, they could represent over 10% US electricity consumption in just 3 years. Powering these data centers also requires a lot of money. Part of that has to do with the electricity that powers the data centers, but also with the emissions associated with this electricity. And in fact, the major tech companies that rely on these data centers are now spending hundreds of millions of dollars to offset their emissions through carbon removal approaches. Additionally, data centers also consume a lot of water. They could consume close to 2% of all US water between what's required to generate the electricity as well as to cool down these energy-intensive buildings. This could pose a challenge as we aim to deploy and expand this important infrastructure into regions that are already facing water scarcity. So then, as we massively aim to deploy and advance AI, we could be running into a future where we're spending billions of dollars in electricity, we're consuming significant amounts of water, and we're producing significant CO2 emissions. But what if we could have, at the same time, a cheaper data center operation, we're actually able to produce water at the data center, and we're able to consume CO2? I think that'd be really wonderful. We can really flip the paradigm. And we can do it. And the first thing to doing it is realizing that a data center is like a toaster. It takes in electricity, and it converts it into heat, typically at around 30 degrees or so. These data centers are, these toasters actually getting hotter and hotter, and that is driven by higher power density hardware, as well as by better cooling technologies, which ARPA-E is also helping develop through the Cooler Chips program. So then in the future, we could have 70 nuclear plants worth of heat coming at higher temperatures between 40 and 60 degrees C, and yet we're not really doing anything with that. That would be like me running my toaster and not putting in any toast and not making any toast. Of course, that does not make sense. So I think we should be making toast. And by toast, of course, I mean carbon capture from the air. And there's a few reasons why I think this is the most exciting toast we should be making. Let's consider a 1 gigawatt data center. Currently, it would require almost $500 million in electricity, would consume 900 million gallons of water, and would emit 1.4 megatons of CO2. All of this in a year. However, say that we grab that free heat and we use that to power carbon capture from the air. We can actually generate $0.3 billion by selling that CO2, effectively having a 60% discount in our data center operation. We can actually produce water instead of consuming water, produce 700 million gallons. So we can turn this into water positive, and we can actually capture more carbon than we emit in that electricity, 1.4 megatons of CO2. So we can turn these data centers into carbon negative. Now, I think this is wonderful, and I think this could be done with sorbent-based carbon capture, where a sorbent material captures CO2 and water from the air. We can then heat up the sorbent to release back that moisture and water, and we can repeat this process cyclically. With the produced CO2 and water, well, we can condense the water, and that's the drinking water that we can produce at the data center. And that leaves behind a pure stream of CO2, which we could then convert to make fuels, polymers, or other advanced materials. However, there's two challenges that prevent us from doing this right now. We actually know how to capture CO2 from gases. We've done that for close to 100 years. However, this is typically done at higher temperatures, above 80 degrees C, with heat that comes from either combustion or electricity. So then if we want to leverage data center waste heat, we need to develop materials that operate at these lower temperatures, between 40 to 60, in an efficient manner. Now, this is a tough task by all means, but I'm excited to see some recent materials that start going into these lower temperatures, such as the combination of amines with covalent organic frameworks and with biomass. However, more work needs to be done to further lower this temperature, to holistically improve these materials, again, prioritizing low temperature performance. And all of this has to be done while keeping an eye on scalability. We're gonna have to make hundreds of tons of these materials. The other challenge is a time challenge. The heat that is generated at the data center can have variability, as it is dictated by the computation happening at the data center. So then how can we have a carbon capture system that dynamically takes this heat in an efficient manner? Well, we might need to schedule some of our computational tasks aware of when our carbon capture system can take that heat. We might need to design and operate our DAC system flexibly such that it takes this heat dynamically. And we might need to build some approaches to reject and store this heat when there's excess. Now, if we solve these challenges, I think there's a massive opportunity. We're able to simultaneously have cheaper data center operation that produces water and consumes CO2. This can enable drastic reduction of emissions at these data centers, as well as supporting and ensuring leadership of the US in AI infrastructure. So if you're working on materials, on data centers, and on these system-level challenges, let's work together, let's unlock the world's largest toaster, and let's grab coffee and, of course, toast tomorrow at Coffee with ARPA-E. Thank you. And with that, I'll let Ben go ahead and explain to us some efficient AI hardware technologies that can make these toasters actually smaller.
Thank you, Carlos. I certainly don't want to ruin breakfast for anyone, but I am going to talk about a new type of data center that might make less toast. My name is Ben Weiner, and today we're going to learn how to go with the flow and use physics-based computing for AI. But first, I want to start with two very important lessons that we can learn about AI from none other than The Hitchhiker's Guide to the Galaxy. The first lesson is don't panic. Generally good advice. But the second lesson is that in The Hitchhiker's Guide, the most powerful computer in the universe is not a data center, it's the planet Earth. And while the idea of a planet-sized computer is science fiction, the reality is that physical processes are transforming information around us all the time. And if we can harness those processes to do some useful computations, we can revolutionize AI speed and efficiency. This is critical because we stand at a crossroads between two futures: AI for energy versus energy for AI. On the one hand, energy innovators like yourselves are already doing amazing things with AI, from testing tens of millions of materials to find the single best battery electrolyte, to optimizing the grid for increased capacity and resilience. On the other hand, data centers could soon consume 10% of US electricity, and in our own backyard, Northern Virginia is known as Data Center Alley. There, the explosive growth of these systems has pushed the grid to the breaking point, to the detriment of that community. Data centers are so power hungry that tech companies are considering devoting entire nuclear power plants just to feeding them. But it doesn't have to be that way if we turn to physics-based computing. I'll define that as hardware that implements algorithms as physical processes. So that's a little bit of a mouthful, but to understand it, imagine that you run the municipal waterworks and your job is to deliver water across town. One strategy might be to use a fleet of water trucks. This is a very flexible strategy, but it's inefficient. You're burning a lot of energy fighting the physics. And this is analogous to how we do computing today. But if the landscape of your city is just right, you might do as the Romans did and use an aqueduct and let gravity carry the water for you. This is more specialized, but it's highly efficient because you're putting physics to work. And this is the promise of physics-based computing, is that as AI has changed the landscape of computing, we have an opportunity to let physics do more of the work for us. There's already been a lot of really exciting progress in building specialized hardware for AI that's more energy efficient. So I'm showing some cutting-edge systems here. On the x-axis, I have the power. On the y-axis, I have the performance. And what you can see is that whether you're looking at really powerful data center systems or really efficient edge applications, the very best hardware is approaching about 10 to the 5 billion operations per second per watt. But the physical limit is 5 orders of magnitude greater than that. And physics-based computing can help us bridge that gap. So over the next few minutes, I'm going to give 2 examples of physics-based computing: thermodynamic computing, which uses noise as a resource, and physical neural nets, which replace math with physics. But let's start with thermodynamic computing. Here, it's helpful to understand traditional algorithms as sort of like a Greek phalanx, in that they're very rigid and deterministic. AI algorithms, on the other hand, are much more like Times Square. They're noisy and random. And so whether you're using stochastic gradient descent to train a neural net to find critical minerals, or using generative diffusion models to identify new battery chemistries, or using Monte Carlo to simulate the grid, all of these algorithms use noise as a computational resource. And we know how to harness noise for more than a century of thermodynamics. So as anyone who's ever boiled water knows, as you increase the temperature, the water molecules become more dynamic until they can eventually escape as a gas. Similarly, large language models, like ChatGPT, are designed with an algorithmic temperature that lets you control how dynamic they are. So at low temperatures, the output is pretty boring. At high temperatures, the output is sometimes bizarre. And somewhere in the middle, it's conversational. But as you can see, we're already using these ideas at the level of the algorithm, so why don't we use them at the level of the hardware? So how would we build a thermodynamic computer? Well, in thermodynamics, we start with a particle, we give it some thermal motion, and then we put a bunch of them together. So to build a computer, we're going to start with a circuit, which generates an oscillating current. We're going to add some noise, and then we're going to couple a bunch of them together. And we can use this to solve the problem of matrix inversion, which sounds esoteric, but is actually a building block of modern computing. It's just the answer to the problem where if you give me a matrix A, I give you a matrix B that returns ones and zeros. So this might sound abstract, but it's actually the foundation of everything from the control systems that run turbines and power plants, to the software that engineers use to design mechanical parts, to the simulations that grids and utilities use to operate the grid. And we can solve it with our thermodynamic computer by simply mapping these matrix elements A to the couplings, letting the system come to equilibrium, and then reading off the answer from the currents. So instead of doing some very complicated algorithm, we just let the circuit come to rest, like water flowing downhill. And because the calculation is entirely passive, there's a potential for a 10x increase in energy and a 10x increase in speed and a 10x decrease in energy. We're not going to increase the energy. So this is already radically disruptive, but we're still talking about using electronic circuits to compute. And we can actually get beyond that with physical neural nets. Here, it's going to be helpful to just think of a neural net as a black box that takes some input and some parameters that you can train and gives an output. So that input could be a picture and the output could be a label. The input could be a new battery system and the output could be a prediction of its energy density. But regardless, we're using silicon to manipulate ones and zeros and do math. But what if we could do it with physics instead? And specifically, what if we could do, instead of pumping electrons through semiconductors, we could shine light through a crystal? So to see how this would work, imagine that you're trying to identify a handwritten digit. You can encode that data and your parameters into the electromagnetic spectrum using a laser, pass it through a nonlinear optical element, aka a crystal, and then read off the transformed spectrum with a camera. So it certainly takes energy to run that laser and that camera, but again, the calculation is entirely passive. And as a result, there's a potential to increase the speed by a factor of 10 to the 4 and decrease the energy by a factor of 10 to the 8. Now, these are only theoretical upper bounds. It remains to be seen how efficient this would be in practice, but the potential here is so great that even if you were off by a factor of 10,000, you'd still be doing 10,000 times better than the state of the art. So physics-based computing has furnished us with some really powerful ideas about how to transform data centers. But what will it take to bring them to a data center near you? The first thing is scalability, which will entail choosing the right hardware. In the example with the crystal that I just gave, you could probably only support a model with a few thousand parameters, much smaller than the ones that we have today. So we need to identify more scalable hardware platforms. That could be spatial light modulators, silicon photonics, crossbar arrays, or something else entirely. I don't have the answer, but that's why we need material scientists, semiconductor engineers, and data center architects to help us figure it out. The second challenge is integration, which means software to tie it all together. Computing is already heterogeneous with CPUs and TPUs. Soon we'll have Emily's optical computing. I want to throw physical computing into the mix. There are related ideas in neuromorphic and analog computing. Quantum computing is advancing by the day. And what we need is software to conduct this symphony of hardware so that you as a user can just specify your problem and get a solution. And that's going to require experts in the software, algorithms, and control systems. So we have an opportunity to get on the path of AI for energy once and for all. But to do so, we need to bring together innovators across this computational stack, from the hardware, to the compilers and the error correction, to the software and the algorithms, to the energy applications themselves. It will not be easy, but if we do this, we can achieve massive energy savings, rapid energy innovation, and US leadership in AI. So if you're excited about this vision or have ideas about how to make it possible, let's talk at Coffee with ARPA-E tomorrow morning. Thank you.
Okay, and now comes the fun part. So please send your questions in by scanning this QR code, and we'll be happy to grill everyone up here and get the answers that you're looking for. Before we get started, I have a question for Carlos. Is the toaster empty? Did you eat your toast for breakfast?
I actually don't like toast.
Oh, okay. Lots of carbs, I get
Yeah, I
it.
know.
It's okay. So I think we can say it's empty, so that's good. No toast was harmed in this fast pitch conversation. As a serious question, though, what would your toaster look like with respect to data center architecture? Is this something that could be built onto existing data centers as a capability, or would it have to be new construction?
Yeah, I think it's a great time for me to call out Peter's program, actually, because Peter's program is doing a great job at cutting energy use at data centers by improving cooling efficiency. Another benefit that we're gonna get from those systems is higher temperature heat. So then I'm eager to see how these systems that Peter's teams are developing can integrate into these heat reuse applications. And I would challenge your teams actually to think about that right now. I know they're here, so I'm challenging them, I guess.
They're working on it very hard. Make sure you go see them today. Some of the teams are going pretty high, 60, 70, but the chips themselves, the packages are getting pretty complicated. So this needs to be worked from multiple angles. We need more use out of the energy that we put in data centers.
Yeah.
So moving on to Peter here, what makes you think that electroactive fuels can be more reliable than diesel gensets?
That's a very good question. It's very important when you have such an extremely large computational problem that each particular core only handles a small piece, that the entire system starts to work as one. And I see both on the power provisions side as well as cooling, which is the other program I run. Cooling, to me, is an energy flip over into another domain, but it's the entire architecture has to be starting to be designed more as a system science. I used to work on aerospace where we designed for 9 nines of reliability, and right now I see the hardware on the power side. It has some engineering architectures to get that safety, but we need to think about what are the true elements if you want to keep all those cores up. And I'll give you an example. Currently we design many data centers with tier 3 or other requirements. And that means if you have 100,000 cores running, there's probably one of them failing all the time. Right? So we have to start thinking about how can we either have cores in backup, make redundancy, and those kind of architectures I think are truly needed if we want to really reach and go beyond the 10 to the 24th in problems. And I think one of the things you'll very quickly see when you do reliability analysis, which I force for my teams to do on the cooling side, is that the more things you have in between, the more components, the more sensors, the more things can fail. So let's try to think about the natural way to power 0.65 volts and not forget that, and think about the natural solutions that line up closer to that. So are these things at scale truly going to be more inventive? More reliable? I don't know yet, but I think they'll a much better natural fit and therefore will reduce component number.
Okay, so now that Peter has figured out how to make data centers secure, it's Ben's job, and we've got a question here about how we're going to do that. So how would you scale these physical neural networks to millions or billions of parameters since Peter's got your back?
Yeah, it's a great question. I think that there's scaling and integration challenges on both the hardware and the software level. I think that, you talked about heterogeneous packaging. That's going to be a huge part of this. I don't think that anything that I talked about is going to replace normal chips and silicon. It's all going to have to work together. So that's a major component. I think that the software is another big piece. Peter is talking about how these are distributed problems. You have to break things up across cores, and our ability to do that sort of constrains how scalable you have to be, right? If you can break the problem into smaller pieces, maybe you don't need to reach a single chip or a single device that can hold that many parameters. So I think there are a lot of challenges on both fronts, but a lot of opportunities.
Well, great, and I'll take one for myself here that I suspected could be coming and follows on nicely to Ben. When will the photons replace the electrons? The answer is never. Both, as we said before, with the heterogeneous integration scheme, the photonic integrated circuits can be part of this, and again, add a lot of value. For specific applications where we just can't put chips with solder right now, so solder melts at approximately 270 C, or that's our upper bound. Anything above that, can we use optical computing? We've got to find a way to get the little connector on there, but we can get rid of that solder and have it freestanding. Also, applications that require good radiation hardness, again, get the metal out and then we can look at those opportunities. But traditional computing is not going away. The optical computing will be part of that ecosystem in that heterogeneous integration scheme. So anybody worried about electrons, we can calm down now. So I'll go back to Peter. What is the scale of that powder paste could reach? Milliwatts of energy, or what type of scale? And how developed is the supply chain?
So the supply chain, I don't know. It's developed by Fraunhofer Institute in Germany. I forgot to mention that their logo was on the slides. But once you produce hydrogen, the PEM fuel cell architectures are at scale already. You can get those at larger scales. I don't think that is something that's, the fuel cell architecture is scalable. The amount of total paste that's being produced at the moment, I don't know. But I really want to see this not as particular solutions. I want you to think about the breadth of the spectrum of solutions that could be explored when we're looking at electrochemistry to power chips.
Okay, great. In terms of other solutions, and again, going back to how we cool these data centers, for Carlos, is waste heat already being leveraged from other sources? And why is direct air capture the best option, not district heating or something similar along those lines? And I know you have a thought on district heating.
Yeah, I think that's a great question. So I'm a heat transfer engineer by training, so I think everybody loves waste heat because there's just so much energy. And as we think of these data centers as toasters, there's just a tremendous amount of energy. Waste heat is notoriously really hard to valorize, especially at these low temperatures. So even if you look at the thermodynamics of what you can do with this heat, I become really excited about carbon capture. I think for me, it's three things. It's generating profit for these data center operators. Carbon capture is going to maximize that. And then turning these systems into carbon negative and water positive, I think it's really flipping the switch, pun intended, on how we can operate.
Great pun, great pun. Gotta love a good pun. So I'll take another one for myself here. Can optical computing be downsized like electronic computing? Yes, very much yes. One of the parts of the downsizing is actually related to the scalability. So the great time and why optical computing is really primed to take off as the next generation topic is because of that silicon photonics scale down, integrating those lasers, making the chips smaller. And we can do that on equipment that is not quite the state of the art, not quite that new. So 200 millimeter wafers, if you've heard of that, humans have to carry those around, whereas 300 millimeter wafers, the state of the art clean rooms and fabs, all of that is automated. So there's some capacity and space in those older wafer technology fabs where we can start to scale and really experiment with how small can we go, but most definitely. And it depends what you're doing. In some cases, it may actually be better to have a larger chip so you can get more optical fiber onto the chip and crank up that speed. In others, yeah, if we can make sensors as tiny and cheaply as we can, then that's really what we have to do to open the doors for geologic hydrogen and geothermal, because no offense to my colleague Rob or others, those are kind of have to be pretty cheap applications. So to help them out, we've got to match that same level. Hopefully Rob is not mad at me if he is in the room. So. For Ben, we'll go back to another computing-related technology here. So what could the role of deep learning-based classification models be in optimizing searching large data sets? So we're using, again, our servers, we're generating heat, but what is the role?
Yeah, I mean, the deep learning revolution is probably 10 years old at this point, since people use deep neural nets to basically solve the image classification back in the 2010s. And so I think that we're now just seeing, the fruits of that, especially as it's being applied to energy problems in industry. But that's the real power of, I think, these new computing paradigms, is that they give us they're doing, I made this comparison, that traditional algorithms are very rigid, but AI algorithms are very noisy. They use stochasticity. We've built all of our hardware for the former. We suppress noise, we make sure everything's very predictable. And then we go to great lengths to simulate noise to use these new algorithms. And so that really is the opportunity, is we've built this amazingly powerful software stack over the past 10 years. So I think our hardware should really start to reflect that so we can fully take advantage of it.
I'm all for building hardware. So along those lines, for Peter, looking at AI energy usage versus outcome, can we eventually expect an asymptotic gain?
Oh, that's a...
You get the hard one. I don't know who submitted that, but good job. It's been #1 on the list. I've been waiting to use.
I don't know. I think it's I never like to project too far into the future. Even the 10%, 2028, these numbers get very big very quickly, or 2030 or 2035. And the human body is about 100 watts, and we use 20 watts for our brain. That's 20%. So if all society starts using 20% for what we call it electricity to intelligence, maybe that's a limit. But at some point, we're going to ask ourselves, is it worth to train these models versus all the other things we could do with energy? So at some point, there's going to be an opposing force. So I don't think anything ever will be asymptotic. And I hope that one day quantum computing will solve at least the training part of the AI models. We still have to manage the inferencing, which might have to be in hot climates where heat management is even more challenging. So I think there's a lot to learn, and there's a real open space, I think, as we start looking at furthermore. What I've truly realized is that building as the status quo will start to creak in all the edges. We need to start thinking about this problem more around what is the software, what is the right hardware, what is the right system, what is the right electrons or photons choice to make.
Yeah.
To tie them all together.
Sounds like there's a lot to talk about at coffee tomorrow. We're going to solve all those problems tomorrow with a cup of coffee, in case you weren't prepared for that. So shifting to Carlos, there's a question about the dilute separation. What would the emphasis be? Would it be quantity or energy efficiency? Kind of like Peter was talking about with brains and what we can do with those.
Yeah, so CO2 in the air is really dilute. That's the challenge, and that makes it a very energy intensive process. People have built these DAC plants, extremely energy intensive, but what if you get the heat for free? What if it's heat that you just have lying there around, and you're tackling one of the biggest cost drivers and energy drivers of this process? So I see it as a really good marriage. You have this very energy intensive process and this tremendous amount of energy, and we're thinking of combining those by enabling the technologies that are needed for that.
So we'll stick with Carlos, and we've got another great question that comes in, again, as a metallurgist. So there's a lot of processes and industries that generate industrial heat. Why is this not a focus area? I mean, we won't put you on the spot for all economic models and business projection plans, but why are data centers a better application for this space than, say, a steel mill?
Yeah, there's many things there's many things that generate waste heat, many things you can do with waste heat. For me, the data center opportunity is tremendous because it's one of the biggest growing industries right now. They have strong interest in being carbon negative, water positive. So that makes a lot of sense. If you're thinking of steel making, there's certainly opportunities there and other, say, industrial processes to use that heat, either for on-site use, but I mean, if you also have higher temperature heat, there's also other opportunities. What I'm interested in is this kind of low temperature, 40 to 60 degrees. I think that's where DAC can really play an important role.
40 to 60 sounds pretty toasty, pun intended, with the toaster. But yeah, that's a definite range that corresponds with a data center. So I'll take another one for myself here. The question is how you anticipate overcoming radiation damage in optical computing. So radiation damage is something that if you have something on a space station, like a sensor, or high up in the atmosphere, or in a nuclear facility, where you would want radiation hardness, you'd still want performance. Part of it comes down to the materials. So the wide bandgap materials, I'll be honest, I don't know the radiation hardness factor, but likely higher, or we could engineer substrates that are more robust. My personal interest is in the optical interconnect, so getting that fiber optic cable and that signal, that data signal, onto the chip. Whatever that chip is made out of If you have right now polymer connectors or plastic connectors, those are not radiation hard or rad hard, as they say in the industry. You can go to a metal a little better, but if you can go to a ceramic, you're in good shape. That's where it becomes more robust in general, because if you're attaching to a silicon chip or a wide bandgap material substrate, then you get more coefficient of thermal expansion or CTE matching. So you've just got a more robust structure overall. A lot of materials work needs to and can be done in this space to come up with optimal solutions that can really literally take us to new heights and new galaxies. No pun there, just a space reference. So. Going back to Peter then, and staying on the hot topic of heat, what's your perspective on air cooling versus liquid cooling for future data centers? And I have opinions on this too that I've shared with Peter many times. So.
I think there's room for everything. But if you look at the density of AI chipsets, which are in the kilowatts space, to cool those with air, using traditional cooling methods, you're going to spend more than 50 or 60% of your energy on the cooling system just to pump air. Liquid cooling, many different variants in that. I hope you all see the cooler chips section of the showcase. Offers you opportunities to cut that energy back by 90 to 95%. And I look at it this way. We started the program as focusing on data center efficiency, but because of the limitations on the grid, I now say, do you want to use 40% of the very dire grid connection? Like say you have a 100 megawatt grid, you want to use 100 megawatt grid connection. Do you want to use 40% of that for cooling or 95% for computing? And that's what liquid cooling can offer you. And it's really reducing that resistance between the chip and the cooling system and allowing that heat to find a more natural path to the outside. It has a lot of challenges. The team's making great progress. When I look at this too, is that number 500 billion, you should not, think about that. I cannot really imagine how much that is. But we heard earlier, nuclear, couple $1 billion. I remember that when we designed jet engines, $2 billion to design a jet engine. That's 100 new jet engine designs. This is a lot of money. And the amount of investment that's going to go into data centers, if we don't do that smart and develop solutions that make this the most compute per power delivered, we can waste a lot of energy. And I think we have an opportunity to get these solutions out and make us lead in that space by a landslide.
Great, and so I will say we're in the home stretch. It's about time for the 2-minute warning. So I don't know, Ben, this may be the last question if you want to talk for 2 minutes. And it is a question we could talk about for 2 minutes. How can physics-based computing be integrated with traditional data centers without requiring a complete infrastructure overhaul? So similar to what we asked Carlos earlier.
Yeah, it's a great question. Look, I don't think this stuff is ever going to scale and make an impact if it's not integrated. I think we're very far away, if ever, from building data centers that are just physics-based computing. But I think, again, if you go back to this idea of heterogeneous integration, a chip that's a neighborhood with many different types of processors working together, that's really going to be the key to making this possible.
Okay, that did not take 2 minutes. So along those lines, or continuing that thought, I think this is something that we hope came through in this fast pitch panel, and based off this question, it sounds like it might have. So there appears to be a natural connection for photonic semiconductors and physics-based computing. What interactions can be explored?
Oh yeah, they're very related technologies. I mean, I would say conceptually, you should tell me if this sounds right to you, but I think the conceptual difference between what we're talking about is that you're talking about doing digital logic with photons. I'm talking about doing new algorithmic primitives, maybe not ones and zeros, sometimes with photons and sometimes with other things. I think there's a ton of synergy, especially at the hardware level. I mentioned silicon photonics. It's one of the most promising platforms for physics-based computing. So a lot of the same, I would say, tailwinds for optical computing. They're very interrelated.
And I'll agree, I think this is a great example why we need all of this multidisciplinary work, I'm used to building things. I'm a materials engineer. Ben's an electrical engineer. They do all kinds of stuff, but in this case, I think he's an electrical engineer. He's giving me a look. Okay,
I'm sorry.
But anyway, he designs circuits, and really the neuromorphic stuff is not to minimize it, but layouts and what we can do within the laws of physics that with the structures we can build. So very complementary, and that's exactly what we hoped came through here, and happy to chat about all these angles tomorrow at coffee. Thank you all so much for coming. Really appreciate the wonderful questions, and don't forget, we have 3 more fast pitch sessions throughout the rest of the summit, covering all kinds of other topics, from energy generation all the way through nuclear. So stay tuned, come see it all, and get a lot of different flavors for what ARPA-E is about.